Friends, welcome back to my YouTube channel. In this class, I am going to discuss about the exergy of a closed system. What is exergy? I have already discussed in my earlier videos. Exergy is nothing but your available energy. That is the maximum useful work that can be extracted from a system in a specific environmental condition. And exergy depends not only upon the property of system but also upon the state of environment. So it is a combination property. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. Exergy is, I can say, exergy is work potential. If you want to define it, exergy is work potential of a system in a specified environment. कितना वर्क कोई सिस्टम कर रहा है वो इम्पोर्टेंट नहीं है. व्हाट इज इट्स पोटेंशियल, व्हाट इज इट्स मैक्सिमम कैपेबिलिटी. सपोज कोई एक सिस्टम right now is producing 50 kilojoule of work, but it has potential of producing 90 kilojoule of work. Then you can say that its exergy is 90 kilojoule, not 50 kilojoule. When is the maximum amount of work is produced? We have already discussed that when the process is executed in a reversible manner and eventually the system comes in equilibrium with the environment. That's when the maximum amount of work can be extracted. Once the system comes in equilibrium with the surroundings, that means once the system attains dead state, then no more work can be extracted out of it. So, any system contains some internal energy, and that internal energy consists of mainly sensible energy, latent energy, and chemical and nuclear. And in absence of these chemical and nuclear reactions, any system contains only these two forms of energy. One is sensible form of energy and another is latent form of energy. And these two forms of energies can be transferred to or from a system as heat. These energies can be transferred to or from the system in the form of heat. And this transfer of heat takes place only if there is temperature difference between this particular system and the surrounding. If the temperature of system is higher than that of surrounding, then this heat will be transferred from the system to the surrounding. And if the temperature of surrounding is higher, then obviously the heat will flow from surrounding to system. It will flow towards the system. But second law of thermodynamics states that heat cannot be converted completely to work. So this whatever energy is contained in the form of sensible and latent energy cannot be completely converted to useful work. So that means we can conclude that internal energy cannot be completely converted into useful work. So जो exergy हम निकालेंगे वो obviously will be less than this internal energy. But how much less? How much less it will be? That's what we want to calculate. Suppose we will consider a stationary system, of course closed system. Suppose we want to find out the exergy of a stationary system, and which is of course closed. There is no mass transfer across the system boundary. Suppose certain amount of gas is enclosed in a cylinder, and this is bounded by piston. Suppose the system is at a pressure of P and its volume is V and its temperature is T. And this system undergoes a process in which it comes to an surrounding temperature T0. Of course, that means the system moves to an equilibrium state with the surrounding. System moves from this initial state to dead state, where the temperature is T0 and pressure of the surrounding is of course P0 and volume you can say V0. And this is the only form of work that is produced during this process, of course. And suppose during this process heat is rejected by this system, and this differential amount of heat that is rejected suppose is del Q. We have defined that exergy is the amount of useful work that can be produced only when the system comes to the equilibrium with the dead state through a reversible process. So, in a reversible process, heat can be transferred through an infinitesimal temperature difference. It cannot be transferred through a finite temperature difference. So how this heat transfer is possible from this system to surrounding, which is at a less temperature, that is T0, and the initial temperature of the system is, this is pressure PVT are the properties for the system at initial state, and the properties with the suffix the properties with the subscript 0 refer to the dead state. So the temperature, initial temperature of the system will be T and the final temperature will be T0. Initial volume will be V and the final volume will be V0. इनिशियल प्रेशर P है एंड फाइनल प्रेशर P0 होगा अगर हम एक्सर्जी निकालना चाहते हैं. तो सपोज डेल Q इज गिवन टू ए हीट इंजन. सो हाउ कैन दिस हीट बी transferred through an infinitesimal temperature difference? Only through a reversible heat engine. If we operate a reversible heat engine which will extract suppose del Q amount of heat from this system, and it produces suppose differential amount of heat, that is del W heat engine, and this piston produces this amount of work del WB useful. What is useful work? This system pushes the piston, but whole of this work is not usable. Whole of this work cannot be converted into useful work. Out of this, some amount is expended in pushing the surroundings, and that work is known as surrounding work. We will come to that. So here del Q amount of heat is given to the heat engine, reversible heat engine of course. Because exergy जब हम निकालेंगे तो you will assume that the process is reversible and the final state is dead state. So here it is a heat engine, and the final temperature of course will be the surrounding temperature. This is surrounding temperature. So you see, first we will do an energy balance for this system, closed system, and of course it is a stationary system having no velocity, zero velocity. So you see, del E in, energy balance principle if you apply, del E in minus del E out is equal to dE of system. This is the energy balance principle and it is analogous to first law of thermodynamics. अगर ये एनर्जी सिस्टम को किसी भी प्रोसेस के ड्यूरिंग ये आता है एंड ये एनर्जी बाहर जाता है, तो नेट एनर्जी जो होता है दैट इज एक्यूमुलेटेड इन द सिस्टम. वो जाके सिस्टम का जो एनर्जी है, जो इट इज ए स्टेट डिपेंडेंट एनर्जी, इट्स नॉट ट्रांसफर, इट इज स्टोर्ड इन द सिस्टम, वो बढ़ाता है सिस्टम का एनर्जी को. एंड अज्यूमिंग दैट दिस सिस्टम इज a stationary system. So when a system is stationary, योर E becomes U, molecular internal energy, क्योंकि जो काइनेटिक एनर्जी और पोटेंशियल एनर्जी टर्म्स आर रिड्यूस टू जीरो. सो we can write this as du in place of de. एंड हियर क्या हो रहा है, एनर्जी इंट्रैक्शन. ये तो कोई भी एनर्जी यहाँ सिस्टम की ओर नहीं आ रहा है, ये डेल क्यू बाहर जा रहा है. सो इन प्लेस ऑफ डेल ई इन विल पुट जीरो, एंड ऑल द एनर्जी इंट्रैक्शंस आर गोइंग आउट ऑफ दिस सिस्टम. वन इज डेल क्यू एंड अनदर इज डेल डब्ल्यू. दिस इज इक्वल टू डी यू. सो यहाँ जो ये इक्वेशन नंबर 1 है सपोज, एंड हियर डेल डब्ल्यू इज नथिंग बट पी डी वी, एंड विच इज ऑफ कोर्स पी माइनस पी जीरो डी वी प्लस पी जीरो डी वी, एंड दिस पी माइनस पी जीरो डी वी रिप्रेजेंट्स डेल डब्ल्यू बी यूजफुल. ये बाउंड्री वर्क का यूजफुल पोर्शन है और ये यूजफुल वर्क नहीं है, ये दिस इज नॉट अवेलेबल, एंड सो दिस इज द अवेलेबल वर्क और बाउंड्री वर्क का यूजफुल पार्ट है P माइनस पी जीरो डी बी, और ये दिस इज यूज्ड इन पुशिंग द सराउंडिंग. सो दिस इज योर यूजफुल वर्क. सो सिंस ये रिवर्सिबल प्रोसेस हो रहा है, we can say that there is a change in entropy of the system, and this will be there is a decrease in entropy of the system. क्योंकि अगर ये हमारा सिस्टम है, ये हमारा सिस्टम है, यहाँ से डेल क्यू बाहर जा रहा है, तो चेंज इन डिक्रीज इन एंट्रोपी विल बी देयर. सो दैट विल बी डी एस विल बी माइनस डेल क्यू डिवाइडेड बाई टी, क्योंकि ये डेल क्यू बाहर जा रहा है. सो you know, efficiency of the reversible heat engine that operates between the temperature T and surrounding temperature T0, ये T और T0 के बीच में जो इंजन ऑपरेट कर रहा है उसका एफिशिएंसी होगा 1 माइनस T0 अपन T. So we know that efficiency is nothing but, so what is the amount of work, differential amount of work that this heat engine produces is del W heat engine divided by heat input is here del Q is equal to 1 minus T0 by T. So I can write like this: del W heat engine, that is the differential amount of work that is produced by heat engine, is equal to 1 minus T0 upon T del Q, and this is equal to del Q minus T0 del Q upon T, and this is equal to del Q minus T0, and this is nothing but minus of ds. This is equal to del Q plus T0 ds, and this I can write del Q is equal to del W heat engine minus T0 ds, and this is suppose equation 3 suppose, and this is your equation 2, this is your equation 2, this one is your equation 1, and this is your equation 2, and this is suppose equation 3. So substituting del Q and del W into energy balance relation, that is energy balance relation, that is equation 1, we get del W total useful. you know, यहाँ जो प्रोसेस हो रहा है इसके अंदर टोटल यूजफुल वर्क consists of 2 parts. One is the useful part of boundary work that is produced by this system, and another is the work produced by heat engine. क्योंकि यहाँ एनर्जी, सोर्स ऑफ एनर्जी तो यही डेल क्यू है ना, ये डेल क्यू आ रहा है, ये यहाँ से जो हो रहा है प्रोसेस में दोनों एनर्जी, दो वर्क प्रोड्यूस हो रहा है. वो एक बाउंड्री वर्क जिसका यूजफुल पोर्शन विल टेक इनटू अकाउंट, बिकॉज एज फार एज द डेफिनेशन ऑफ एक्सर्जी इज कंसर्न, द मैक्सिमम वर्क पोटेंशियल और मैक्सिमम यूजफुल वर्क दैट कैन बी एक्सट्रैक्टेड. सो सराउंडिंग वर्क को नेग्लेक्ट करेंगे. यू नो, वन इंपॉर्टेंट थिंग इज द surrounding work exists only for a closed system where there is certain change in volume, there is displacement of boundary here, and in case of steady flow device this work is 0, and in unsteady flow, that in that case also the useful work concept will be used and some surrounding work will be there. But in case of steady flow device, this term will be 0, there will be no surrounding work. So substituting del Q and del W into energy balance relation, we get del W total useful जो हो रहा है, it consists of two parts. One is del W heat engine plus del WB boundary work का useful part. So this will be equal to del Q plus T0 ds, and this is from equation 3. You see, del W heat engine will be del Q plus T0 ds. From this equation, del W heat engine will be this, will come to this side with plus sign, del Q plus T0 ds equal to del W heat engine. So in place of del W heat engine, I will write del Q plus T0 ds, and in place of this, this is del W total useful is del W heat engine plus del W B useful. So del W B useful जो है वो होता है हमारा P माइनस P0 dB. del W B useful यहाँ से इक्वेशन 2 से इसी del W B useful is this one, P minus P0 dB. P is the pressure of the gas and P0 is atmospheric pressure. So this due pressure difference, always there will be some absolute pressure. So positive absolute pressure, that means pressure will be in excess of atmospheric pressure to get some useful work. So this will be P minus P0 dB, and so it can be del Q plus P dB minus P0 dB plus T0 ds, and this is equal to, in case of from relation 1, from equation 1, we can write this is nothing but minus du, minus du. You see, from equation 1, del Q plus P dB is how much? From equation 1, you see, minus del Q minus P dB is du. This is the total P dB work produced. This takes care of both surrounding work. Del W here is, this consists of useful work plus this surrounding work. So while using energy balance, this del W consists of two parts. So du is this much. So del Q plus del W will be minus du. So that means here del Q plus P dB is, P dB consists of both parts, useful form, because P dB is P minus P0 multiplied by dB plus P0 dB. So P dB is not the useful form of work. This is the boundary work or displacement work. So if you take the del Q plus P dB, it will be minus du, because we have already taken du here from energy balance principle. du is minus del Q minus del W, मतलब ये minus P dB है. So from this, minus du minus P0 dB plus T0 ds. So this is for differential process. So on integrating, we will get that this is the del W total useful work, that is during a differential process. So for total process, we will integrate this W total useful. This is the your exergy. So this is, we just integrate this term by term. जैसे कि माइनस डी यू का इंटीग्रेशन करेंगे, एंड इनिशियल स्टेट विल बी हैविंग द वैल्यू u and final state is u 0, that we know. This is the final state is dead state. Similarly, in case of minus p0 integration of dv, initial volume will be v, final volume will be 0, surrounding volume. So another term will be plus t0 ds का integration, initial state is s and final state is s0. On integrating this, I will get, so finally I will get u minus u0 plus p0 v multiplied by v minus b0 minus t0 multiplied by s minus s0. And this is the total useful work delivered as the system undergoes a reversible process from a given state to dead state. But we have neglected here the kinetic energy and potential energy possessed by a closed system, by assuming that this is a stationary system. Like in all closed systems are not stationary systems. Assuming that it has some kinetic energy and potential energy, we have to add those kinetic energy and potential energy terms, and that will be your exergy. If you make an analysis of a general closed system, not a stationary closed system. Of course, in case of a stationary closed system, those kinetic and potential energy terms may be neglected. So for a general closed system, this exergy, which can be denoted by x, exergy is usually denoted by x, and this is equal to u minus u0 plus P0 multiplied by V minus V0 minus T0 S minus S0 plus mc square by 2, where c is the velocity of this closed system. Since we have used V already for volume, so we can take c for velocity, and velocity of a dead state is always 0. So this will be mc square by 2 plus mgz, where z is the elevation of the system. And most of the cases we neglect these two terms. So that's why we can write this equation for a stationary system. And if you write on a unit mass basis, and this can be, you can use that quantity called phi, availability function, on a unit mass basis. This is for the total system, total mass of the system. On a unit mass basis, this will be small u minus small e0 plus p0 b minus b0 plus c square by 2, and of course, there is another term minus t0 small s minus s0 specific entropy plus c square by 2 plus gz. And if you take those potential energy and kinetic energy into account, in place of u minus u0, you will have e minus e0, e minus e0. So, exergy of a system which is at dead state is always 0. That means at that point, u will be your u0 and v will be v0. So, this whole equation, all those terms will be 0. And c will also be 0 when the system is at equilibrium with dead state, means its velocity will be 0. And v, in place of v we will have to write v0, in place of u we will have to write u0, s will be same as s0. So exergy of a closed system at dead state is 0. And suppose a closed system undergoes a change of state from 1 to 2, then what is the change in exergy? That will be delta x, which will be nothing but x2 minus x1, and that is equal to m multiplied by phi 2 minus phi 1, and this will be u2 minus u1 plus P0 multiplied by V2 minus V1 minus T0 S2 minus S1, if you neglect potential and kinetic energy terms. So that's all. Thanks for watching.